Let's talk about the transformation defined by the standard matrix. So first and foremost, we have multiple ways to write said transformation, right? We could write T of some vector, we'll just go ahead and call it this for now, is equal to that standard matrix times that vector. If we're going to write that, we probably want to know what the heck this matrix does. Like, what is our domain and codomain? We know if we're talking about linear transformations or even functions in higher level mathematics, we need to define our domain and codomain. So we have to think about this and realize, okay, with matrix multiplication, if I'm multiplying a 2 by 4 matrix by something, I know what I'm multiplying by has to match in terms of the number of rows to the number of columns of my standard matrix. So I must have a 4 by 1 vector that I'm multiplying by here. This has to be an x, y, z, w, however you want to write that. So, and the result is going to be 2 by 1. So we are having our t is moving from a domain of R4 into a codomain of R2. Cute. So if I wanted to be even better about this other way that we just wrote this, I could, I'm going to need big parentheses and a little more space. I could write my x, y, z, w is equal to a times that vector. So that's one way, right, to use the standard matrix and matrix multiplication to define our transformation. I could also go ahead and define this transformation based on the transformations of the standard basis vectors. So in R4, our standard basis vectors are, I'll be good about them and actually write them out, 1, 0, 0, 0. And if I did that multiplication, I'm just going to end up with 4, 0. We have T of 0, 1, 0, 0. That standard basis vector would map to 0, 1. And then we can continue on 0, 0, 1, 0. And these are just the corresponding columns of that vector, that standard matrix, right? Like easily distracted, can't do two things at once. Cute. So that's another way we could have written this transformation. So we have 1 with the matrix multiplication, 2 defining what happens in terms of transformations to each of our standard basis vectors, and then we could go ahead and do 3, write this as sort of that, I don't know, linear equations that happen, right? This is the way that we started this whole section with, sort of recognizing that, okay, if this was some x, right, some y, some z, what happens to each of those things is, well, I'm going to end up with 4x minus 3z plus 2w, and then, oops, I need to do TF first. I got distracted. I really wanted to just jump to the answer. This is, sorry, 4x minus 3z plus 2w, and y plus 3z plus w. All right, so those are the different ways that we can express our transformation, this linear transformation. But let's also talk about what we can now say about that linear transformation in terms of AT3 and AT4. So let's break this down into our image and kernel. Now, looking at this right away, we should recognize that the first 2 columns of my standard matrix, right, those have zeros for each of the other components. So I know these are linearly independent. There's no way I can write 4, 0 as a multiple of 0, 1. So those 2 are linearly independent, and because they're linearly independent and we're in, right, we only have 2 elements, the other 2 vectors have to be dependent on them. In fact, I could easily come up with ways that I could get there, because I just need to multiply that second vector by 3 to get the 3 in this third vector, and I need to multiply the first vector by like a negative 3/4, right? But still, I could do it. So let's go ahead and rewrite this with our reduced to echelon form, because it'll take us just a single step to do that. So if I wrote out the reduced to echelon form of this A, all I need to do, because this is pretty much perfect, right? I have the pivots are descending to the left, or whatever the heck the words are that we use there. Everything in pivot columns is all zeroed out. The only issue is that the pivot in our first row is not 1. So we can multiply through by a 1/4, right? Use that one elementary row operation to find that this is 1, 0, negative 3/4, 1/2. And we get fractions, which is something that happens a lot, not necessarily in our TBIL examples. They're pretty nice to us, but totally reasonable. Okay, so now, if we wanted to, we could write out the image of A, right? Our range of A. I like to do this with span because I think it's kind of the easiest way for when we're talking about image. Now, I could use the original 2 vectors. I recognize those 2 column vectors. I recognize that I don't necessarily need to. Either way, right, I can span all of R2 with either one. So in this case, I'm using 0, 1, and 1, 0 because I'm just spanning R2, so why not do it with the standard basis vectors? This can be something suspect, right, if we have different columns with more components, but that's neither here nor there. Okay, so we got our image. And so let's talk about also those 2 independent and 2 dependent. That should get us to that rank and nullity, right? We have rank and nullity is equal to the dimensions of our domain. So we're looking at rank plus nullity is going to equal 4, right? And so rank is the dimension of our image, in this case 2. That's our 2 linearly independent columns in our standard matrix. And then we also need to talk about these linearly dependent, which we know is related to our kernel. Because the idea here is we had 4 bits of information. We are keeping 2 of them, and then we're going to have to compress, like throw away 2 of them. That's they end up in the kernel. So we'll solve that kernel. We'll figure out what our kernel is by solving the corresponding system of homogeneous linear equations, right? Assume there's like zeros on an augmented matrix here, and we can go ahead and I find the kernel easiest to write doing the work that we did for EV7. So we're going to have, oops, I need to make this way longer. Let's scroll. Right, kernel is going to be an R4, so we have 3/4 A plus 1/2 B negative, oops, minus 1/2. Negative 3A minus B, A, B for A and B within the rails, right? So again, if we wanted to, we could also write this as a span because we have all these different ways that we can write our spaces, right? So I could write down the 2 corresponding vectors for our A and our B's. We have those linear combinations all in here. Boop. Cute. All right, so we can see the nullity of this is also 2, that rank of our kernel. So basically we're keeping 2 pieces of this information, and then we're tossing 2 away. 2 are getting lost into that kernel, which has to happen. We could only do worse than this, right, and keep a single bit of information and toss away 3. Okay, and let's talk about this. Because our image spans all of R2, right, our image is R2, these are the same, we get to say that this particular linear transformation is injective. And because we have anything in our kernel, that means that I have an infinite number of ways to solve any vector I would want to solve in R2 because I have these free variables of Z and W. Because of that, we could say this thing is not, oh my God, I wrote injective, surjective. I described onto, but I said injective. This is not injective. I'm not making this video again. This is what we're going to have. So definitely surjective. We span our entire codomain. We can get to everything in R2. We could also see that by the fact that our number of pivots matched our number of rows, but it cannot be injective. Honestly, the moment we knew we were moving from R4 to R2, we knew that we had to have some dependence between those column vectors, which means there would have been an infinite number of ways to solve things.